Hey all, today I want to talk about serial interfacing. So before I get deep into serial interfacing, I'm also going to be discussing a bit more about serial interfacing and a bit of parallel interfacing. I'm just talking about the differences between both. So in serial interfacing, if you have a device, if you have a transmitter and you have a receiver, and for example this is the byte between them, so it can be like 101. It's gonna first read it at a one bit at a time. So it's gonna read 1, then it's gonna read 0, and then it's gonna read 1. So first when it's 1, it's like the value is 1 itself. With the 0, the value still remains 1, but with the 1 added, the value changes to 5. So there's how a serial interface would be like. A good example of serial interface is Ethernet cable. So the Ethernet port that you have for accessing the internet is a good example of a serial interface, and also a fiber channel. Now let's talk about parallel interfaces and what exactly are they. So if you have a transmitter and you have a receiver, the transmitter will have several buses that connects to the receiver, and each of them provide all the data together. So if it's sending as 101, the receiver will get all of these bits at the same time, bits at the same time, and it's going to be interpreted the same as 101, which is equal to 5. So here the parallel interface and the serial interface are transmitting the same value, but obviously the way they are doing is different. A good example of parallel interface would be a printer. If you look at your printer, the printer would have its printer port would have something like this. It has you can see that it's a parallel interface structure similar to this one. Now we're going to talk about the different in serial interfacing. There are different types of graphs. You could see the types of methods to send the information. So we have the on and off, non-return to zero. Off and on, okay, non-return to zero. We have bipolar. We have Manchester. We have differential, and we have non-return to zero inverse. The I stands for inverse. All right, so in an on and off, you would simply, if your bit the bits that you want to send to your receiver is something like this, and on the graph you would just do 1 0 1 1 0 1. It's pretty simple. However, if you want to do it a bipolar, which is a part of non-receive zero, non-return to zero, it's gonna go like this, then it's going to go negative to represent a 0, and then it's going to go again positive to represent a 1. So this would be 1 0 1. So this is the bipolar, and this is just the on and off, the standard. A lot of times when they're testing you, for example, this is the most common thing that we know and we understand, and it's really easy for us, these both. The other ones are a little more tricky, but we still can understand them. It's pretty easy. So Manchester. Awesome. So if you're going to transmit 1 1 0 1 0 0, let's see how we're going to do that. So when it's 1, we start from 1, and so this is 1 bit, 1 bit, 1 bit. We start from 1, and the midway of that bit we're going to switch to 0, and for 1 again we're going to start again from 1 and switch midway to 0. For a 0 we're going to start from 0 and go to 1. So it's always alternating to the next one. So eventually you're gonna have a wave that looks like that. So for a 1, you again start from 1 and return to 0. For a 0, you start from 0 and return to and go to 1, and for 0 again you return back to 0 and then go to 1. So this is how the wave for Manchester would look like. Now let's talk about differential. In differential, an edge means 0 and a no edge means 1. So if I have 1 1 0 1 0 0, to represent a 1, I do not need an edge. So if I'm starting from here, for example, I'm just going to continue. A 0 is here, so I need to make an edge. 1, continue, 0, edge, and then edge. If that makes sense. And the same for NRZI. An edge represents a 1, and no edge means 0. So if we have the same one above, we're going to be, okay, so edge is 1. So if you're here, it's going to be edge, and then edge, and then no edge, then edge, then no edge, and no edge. So that would be how non-return to 0 would work. So now let's talk about transmitting the bits. So we always have a start bit. Usually you start that denote with that 0. You have 7 data bits and a parity bit and 2 stop bits, which are usually denoted as 1. So parity bit, stop bits, and a start bit. Okay, that's great. So now let's learn about how the start bit, what's the overhead on this particular serial interface. So we have, so we have 7 bits being transmitted, out of which 4 of them are overhead. So the start bit is considered an overhead. Basically, an overhead is an additional information that you need to provide the receiver to make sure that the transmitter is transmitting it properly and it's being received correctly by the receiver. So the overhead in this is start bit, 2 stop bits, and 1 parity bit. So start bit, stop bit, and 2 parity is equal to 4. And we have 7 of data transmitted, so it's 4 by 4 plus 7 is equal to 4 by 11. So basically the overhead is this much. Okay, so now let's some of the 2 common errors that are often encountered when transmitting data is parity and overrun error. What happens in parity? In parity, the parity bit is not incorrect. It doesn't reflect to what is given as a data. And in the overrun, what happens is when we're counting, we're like, hey, things don't really add up. I'll actually talk about overrun a bit later, but let's talk about parity first. It's really easy. So we have a start bit, then 1, 2, 3, 4, 5, 6, 7 are 7 bits of data. I'm going to continue and make a parity bit 1 and 2 stop bits. It has to be noted that the parity is even parity usually, but I think it will be specified in the question what type of parity it is. So in this situation, we have 4 even. 4 even means the 4 even bits, high bits, meaning that a parity should be represented as a 0. So that means that this is incorrect, as a parity is being represented as a 1. So this fails the parity test. Now overrun. So I'm giving you a signal, and according to me, it's complete. So I'm giving you a signal to start. Okay, so in total we only need 11, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so I said earlier that we usually denote our start bit from 0. So this is our first start bit. Okay, so then 1, 2, 3, 4, 5, 6, 7. A parity should be correct because of 4 even bits. But hey, there isn't any stop bits. And had we if there are not any stop bits, so basically that's a huge flag saying that maybe something's wrong with the transmission. Maybe if I give like 2 extra 2 bits, so something like that. Over here, our stop bits are not exactly the 1-1 standard that we expect. So that means something is wrong with the signal. Maybe it started early, maybe we started like sampling early, maybe it started sampling late. So this is considered more of an overrun error. That's one of the issues. And let's talk about in serial interfacing, we normally have two methods. So this topic is over, and in serial interfacing, we have two methods of knowing whether what we are saying, giving is okay. So we have something called as HDLC and bisync. The HDLC is really simple. So it really says that if you ever see 5 consecutive ones together, just add a 0. That's it. There isn't anything to it. So for example, if this is my signal, do I add a 0 to it? No, I do not. And if this is my signal, so I have 6 consecutive ones. 1, 2, 3. So I'll just add a 0 here. So 5 consecutive 1, after that you just add a 0. Period. Nothing else, nothing special, everything's done. In bisync, it's usually that after a DLE, data escape character, does that sound DLE? Okay, one other thing to note that before I continue on this is during the questions you'll be given stuff like 07E or 03 0x. You'll be given hex numbers, so it's going to be 03A. So you have to take 7 and convert it to binary, and I hope all of you are aware about how to convert 7 into binary, then an E to binary, and then convert I think I wrote B or 7 here or 4, I'm not sure, whatever this is. What if this is a B, convert it to a binary, A, convert it to a binary, and then have a look at it. Are there any sometimes things overlap, so this the binary might end up with double ones. Well, it should, because it's an E, right? Yeah, no, that's gonna be F. So if it was an F, it's gonna be ending with definitely like loads of ones. So, and if this is a B, it's gonna begin with 1, I think. So there will be definitely a situation where we're gonna need a 0 between this, and that's what HDLC is gonna help us with. In bisync, if we see in a question, it's going to be saying that, hey, these are some of the characters that are important, and these denote X, Y, and Z, and it's gonna be given in the question. So it's gonna be like, hey, DLE is denoted by 0 to A, and XYM, like for example, I'm just saying XYZ is denoted by 0M 0XB. So if I ever come across 0A and then 0B, what I'm going to do is, first of all, you have to convert it to binary. So once you've converted to a binary, I'm just going to say everything in hex mainly because it's going to be easier for me. I'm going to go through examples later to make sure you understand how to do it in binary. But for in this situation, so you are given this signal, and your data escape character is this, and your XYZ character is just some random character that you need to escape, is considered by a B. So you see an A and you see the B. So what you're going to do is you're going to put instead of your signal being AB, you're going to put it as A, and since A is a data escape character, you need to add another data escape character after this, A. So you're going to put 2 A's, and then B, which is some character which we need to identify separately, so we have to put another data escape character after this. Let's extend the signal. So 7 is not in this table, so we just write 7 the way it is, and 8 is not in this table, we write 8 the way it is. E is not in this table, so we write E the way it is. Let's add F here. F is in this table, so we write F, and then we write a A behind it. So I think I told the basics of the whole serial interfacing, and I hope this was helpful. This is a very short overview of the whole half of the chapter, and that was my main aim, to get everything done really quickly so all of you can focus on exam. Thank you.